All right. I hope the sharing works. I have to apologize. The slides are still mostly in German because in previous years I gave this course in German, but I hope with me speaking in English, this is still okay. In any case, the equations are, of course, the same. So we discussed screen. All right. So we discussed the chemical potential last week, and let me step back once more. Before that, we revisited the first Holmberg-Kohn theorem, which we had already discussed in the chapter 5 on the quantum mechanical molecular applications of quantum mechanical theorems and in the context of the electron density. So this is just a revision, and now you have it also in terms of a slide. Now the second principle states that there's also a variation theorem in your electron density. So there is some energy functional of some trial electron density that will be larger equals E0. We then proceeded to discuss the chemical potential, and in particular we used this the functional derivatives here in this variational principle with the constraint that your number of electrons must be conserved, which is of course crucial. You can imagine that you optimize the electron density somewhere, but then you're losing electrons, so you need to include this constraint for the electron number. So this is then a new auxiliary energy functional, and then we want this to be variational, so we have to consider the total differential. And if your total differential, which in thermodynamics you normally symbolize by the Latin small case letter d, if that differential involves continuous changes in the variable rather than just discrete variables, right? Then we write it in this Greek small letter delta, okay? So that basically means you have a continuous spectrum of variables. In other words, you can very specifically imagine that your electron density sits at every grid point in real space. And so in every one of these grid points, you can vary the electron density. So you would have as many variables as you have grid points, right? And that is, of course, conceptually something very different than a discrete variation in free variables like pressure and volume or something like that. And so the convention is to use this Greek letter instead. But in terms of practical calculation, all what that means is that in your sum over chain ruled derivatives with respect to all your degrees of freedom, this sum simply becomes an integral, and so like this you have the continuous expression here for your functional derivatives. Now there's the lemma of variational theory that if you have an integral like this, this variation in your electron density, of course, cannot be zero, and so this bracket has to be zero to generally have the entire equation free to be zero. Now you can prove this. We are not going to do this. There's a mathematical proof. And this is part of variational theory. but this you'd have to believe me. And if this bracket is 0, this of course means that your mu, this chemical potential or this Lagrange multiplier, is the functional derivative of the energy with respect to electron density. And now you insert equation 1, and then you find that this becomes the external potential and the functional derivatives of T and V. So the external potential we know, right? And the question is also then what are these other terms? And if you don't know these other terms, you cannot really evaluate this chemical potential, and this means you cannot really calculate the energy, right? Because that's part of your job here, to impose this up here, and only then you can get equation 1 really explicitly. And so this is the trick, or the problem in DFT, that we don't really know the explicit form of the exact explicit form of all the terms in our energy, or in other words, we don't know how the operators should look like that act on your electron density such that you recover your energy. Now, this was a big problem, and the one way out, which is unfortunately only approximate, but still very helpful, was the introduction of the Kohn-Sham Potential, or the Kohn-Sham Ansatz. Now, the Kohn-Sham Ansatz sort of does a U-turn, and we go back to the idea of electronic electrons and their orbitals. Okay, so we introduced this electron density, and it's wonderful. It only has 3 dimensions. It's independent on the dimensionality of your problem is independent of your number of electrons. And now, because we don't know the expression for the energy, we go back to what we do know. And we do know the Hamiltonian for electrons, for orbitals, right? So we reintroduce now again 1 electron orbitals, okay? Very much like in Hartree-Fock. In fact, we actually use the Slater determinant to expand these orbitals in order to ensure Pauli again, automatically. So what we did in Hartree-Fock, what was so great, we want to keep that. Okay, let's not sacrifice progress we have made in the past. Let's make use of it. Let's build on it. Right? That is a better strategy in general. And so that is what is meant by or implied by when you talk about the Kohn-Sham Ansatz. But the Kohn-Sham Ansatz goes beyond that. Okay, and let me explain you how. What we do now is to write down for every electron a single electron Kohn-Sham equation, and this is a single electron Schrodinger equation, really. Right? So this is, here you see some Hamiltonian operator, and out comes your eigenvalue with the electronic wave function. So this is identical with Hartree-Fock. Right, the left hand and the right hand side expression in equation 5. However, in the middle, you have something different. This is not the Fock operator. This is a kinetic operator. And then you have this Vs. This is some unspecified potential. Right? We call this the Kohn-Sham potential. So that's why the S stands there. So the Kohn-Sham potential, Vs, is not specified, but, and it's not written here explicitly, it is a functional, again, of the electron density, okay? Which means, again, as in the Hartree method already, you will have to do a self-consistent field loop on this, okay? So again, it's a mean field method. DFT is a mean field, just as Hartree-Fock, okay? So this is a very generic expression. if you drop the S, right, then your Hartree equation can be written like this, and also your Fock operator is also effectively an mean and averaged potential. So it's very much very similar in nature, right? Now, these Kohn-Sham orbitals are orthonormal eigenfunctions of this operator, and they have to meet all the conditions of the 4 equations leading up to equation 6. Okay. Now, the first one is easy for you, right? In our theorems, we discussed this, right? So orthonormal eigenfunctions, this is a nice thing. The electron density, we already discussed this as well, is just the sum. I dropped this, but it's just the sum over the occupied. So this capital N is the occupied orbitals squared, right? They are orthonormal, so this will be the number of electrons here, this N. And so if you integrate over all of this, you must recover the number of electrons. And now if you look at this equation here, you multiply from the left with your phi I and you integrate, then you have your epsilon I, and you do this for every electron, right? And then for every electron you get a kinetic energy. So the total kinetic energy is your Ts, the Kohn-Sham kinetic energy, and you get this contribution from this Kohn-Sham potential, this Vs. Now, one very important difference to Hartree-Fock is that the Kohn-Sham potential, as you see it here, is just multiplicative. Right? The exchange potential in the Hartree-Fock operator is not. Right? So we discussed this also. It introduces this non-locality and so on. So basically, you can view actually the Kohn-Sham potential as something that should appropriately be placed in between Hartree and Hartree-Fock, right? It's something in between. It's more approximate because your Kohn-Sham potential is just multiplicative. In fact, it turns out, and we will come to that later on this week, that if you blend in Hartree-Fock with the Kohn-Sham method, you still get a lot of accuracy gains, which is extremely helpful for your predictions, while hardly increasing the computational cost associated to that. So in some sense, these methods are actually called hybrid methods, so some sort of Frankenstein, if you wish, between Hartree-Fock and Kohn-Sham currently yields some of the best predictions, numerical predictions of chemical properties in quantum mechanics. Now, so these equations here must hold true whatever you do, okay? Now, what's very important also to note is that this kinetic energy here, right? This was historically one of the main reasons why people went back to the electronic orbitals as implemented in this Kohn-Sham Ansatz. So in this expression here, your kinetic energy here, the true kinetic energy, right? Not just the Kohn-Sham kinetic energy, the true kinetic energy is the biggest unknown. Right? For the electronic interactions, you can already assume some easily assume some Hartree repulsion, and that models it to a great deal, and then some small part is missing, and so you can think of some exchange there, right? So we know, we have some feeling about that from Hartree-Fock, but the kinetic part was the major, the largest term that was unknown, and the approximations that were developed over the time to this kinetic energy term were so poor that it was really a necessity to introduce the orbitals again within the Kohn-Sham Ansatz. Now, we can write the electronic energy within Kohn-Sham exactly in this way, where we say we have our energy from the external potential with some electron density, and we have an electronic universal functional, capital F, which consists of the Kohn-Sham kinetic energy, the Hartree repulsion of the electrons, right? So the classical or Coulomb repulsion, it's the same thing. So classical electron density repulsion, which imposes overcounting, and it also imposes lack of quantum behavior. So this does not know about Pauli's exclusion, and it does not know about its only mean, right? So it doesn't have electron-specific correlation terms. And then we say everything else, basically the dirt, we put under the carpet now, okay? So all other terms we are missing, all physics we are missing, we put in this dubious term called XC, and XC stands for exchange and correlation, right? We know from Hartree-Fock there should be exchange terms, right? This is exactly true. And then from Hartree-Fock, you're still missing correlation. So these two words are used to describe this. Actually, what always bothers me is that you certainly have exchange effects missing in this, right? So they should be in there. Your potential is just multiplicative. The Kohn-Sham potential is just multiplicative. There's no exchange. So you need to somehow effectively include this physics into that multiplicative potential, right? So you certainly have exchange. Hartree-Fock is not exact. You're still missing electron correlation. So you certainly have correlation. But what you also have, and that's actually different physics, what you also have is the difference between the true kinetic energy T and the Kohn-Sham kinetic energy TS, okay? And that is sort of missing, right? I think there should be really an EXCK for exchange correlation and kinetics, but the convention is as such that we call it EXC. Now, this first term is trivial, right? Your kinetic energy is just the sum over the expectation values of your molecular orbitals with the kinetic operator, where these orbitals correspond to the orbitals that will contribute to the entire electron density, for which the energy is minimal. So this min thing basically means you should be using the optimal orbitals, right? So after your SCF, then your kinetic energy according to Kohn-Sham is this thing. And then the classical Coulomb, or also known as Hartree term, is just like that. So you know this. And again, be aware of the overcounting, right? Here you have electron density at R, and here electron density at R prime. These electron densities partially come from the same electron, right? And so this is just like in Hartree-Fock, and in Hartree you're overcounting things here. And then, as we said before, this exchange correlation term is the difference to the true kinetic energy and the difference between Hartree and the true potential electron-electron interaction energy. Now, now we basically have everything in this framework, but one thing, okay? The one thing which we don't have is the explicit Hamiltonian. What is this Hamiltonian now? Okay, how does it look like? Right? So this is something we can derive now, and we exploit for this the variational principle. Okay, so for very small variations in your electron density, then you have your differential of the Kohn-Sham energy, and it contains this kinetic part, and then it contains the external part, the Hartree part, and this exchange correlation part, right? So we basically keep the kinetic part implicit here, and we apply our functional derivatives here for the potential parts, right? So for this one and for these two guys, okay? These, the VH is just the functional derivative of the energy, of the Hartree energy, and the VXC is just the functional derivative, the exchange correlation energy, and that's unknown, right? We didn't specify that yet, okay? Now, this is one of the frontiers of science. If you could come up with the true exchange correlation potential, you would most certainly be an immediate candidate for the Nobel Prize. Okay, there's no doubt. Now, many people have been trying to do this, and great progress has been made, but so far nobody wrote down the exact exchange correlation potential. As we also discussed previously, chances are it's incredibly complicated. Now, you can solve this delta Ts. You can solve for it, right? And use the Kohn-Sham equations, right? So so from this, right, we have Ts, right, and we know that this holds. So Ts, this this integral of electron density and Vs gives you the electron eigenvalues, and these electron eigenvalues is what you see on the left, right? These are the expectation values of the Kohn-Sham equations, and they must be equal T plus this. And if you now vary, then you find correspondingly that the variation of this part here must then yield Ts dt to be this, right? And so we can use this expression here, the negative of your Kohn-Sham potential with the electron density. We can substitute it in here, okay, in equation 10. So this substitution then means that the variation in your energy is this. And now you might see this already. Now we have in both integrals, which go over the same domain, same spatial domain, we have our variation in the electron density, which we can factor out. And this means that the resulting bracket here, this one, has to be equals minus Vs. No, the bracket has to be equal. So this minus Vs has to be 0 for the variational principle to hold, and thereby you have identified the Kohn-Sham potential as your external potential, the Hartree potential, and this exchange correlation potential. So the Hartree potential is sort of very intuitive. The external potential is very intuitive. And you see now it's extremely elegant. All you have to do is come up with some approximation to this exchange correlation potential. If you have this approximation, you plug it into your Kohn-Sham equation, right? And then you get, by an SEF, you get the energies and the molecular orbitals, you plug them in here, and then you can calculate everything. So this Kohn-Sham potential, of course, depends on your electron density. And so you have to do this iteratively, as we just said. So what happens then with the energy, right? How do you calculate the energy? If you, once you do this SEF with this Kohn-Sham potential, and assuming that you approximate somehow this exchange correlation potential, so for the energy has to be minimal. Again, so we can write our energy in this form, where we know that our kinetic energy is also in here, right? And this must be with this, so we can substitute this, right? That's what you now see here. Actually, I'm afraid here is there's a typo. We forgot the plus here. But anyhow, so this equation is correct, right? So now you have the Kohn-Sham potential integral and the eigenvalues in here. Now let's consider these two integrals in the beginning, and the last three terms we call this rest, right? Then you can factor out this electron density, and you can also substitute your expression for the Kohn-Sham potential. And then you see that the Vx, the external potential, exactly cancels. And you are left with two integrals. One integral is simply the Hartree energy integral, or twice the Hartree energy, right? So you see this here. And the other one is the integral of the electron density with your exchange correlation potential. And then you also have the rest, right? So you also have to calculate the eigenvalues, and once more the Hartree energy and the exchange correlation energy. Now you have -2 times Hartree plus 1 Hartree gives you only -1 Hartree. Then you have the energy of the exchange correlation potential, this is small v. You also have the energy of the exchange correlation, right? These two are not the same. Actually, when we discussed the virial theorem, we mentioned this. Only and if only your exchange correlation potential was a homogeneous function, then these two would be related by a simple factor of the degree of your homogeneous function. But this you cannot necessarily assume, okay? So by default, these two are not the same, and in practice, they usually are not. And so this is then how you see your energy. Your energy is the sum over the eigenvalues, and then you have this whole bunch of, so the difference between the exchange correlation and potential and the exchange correlation energy, and a double counting Hartree term, which you have to subtract. All right, so to reiterate, what is the procedure? The Kohn-Sham equations are being solved iteratively until self-consistency, right? So you plug in some initial electron density, then you get a Kohn-Sham potential, and then you solve for the molecular orbitals, and then you get a new electron density, and you keep on doing this. There is a proof that the exact Kohn-Sham potential exists, right? But unfortunately, it is unknown, and so we have to approximate it. It's very important. Similar to Hartree-Fock and Hartree, all these orbitals and eigenvalues are not real in the sense that they only approximate the true eigenvalues. right? And they are models that have a fair degree of arbitrariness. One thing is, for instance, you can apply unitary transformations to all your molecular orbitals, and the eigenvalues and the energies will not change. Okay, so your orbitals can change in shape, but your system stays the same. This is important to remember. What is the true observable is, of course, what you approximate in terms of the total expectation value, right? So that is something that does not depend on your particular eigenvalues and orbitals. So in this sense, there are many, arbitrarily many solutions which would all result in the correct, or in one energy estimate, total energy estimate, but so you cannot really assign too much meaning to these. Now, the fact that there are many solutions does not mean that these solutions are meaningless, right? Or that they are useless or wrong, right? It's just that there are many ways, right? So think about it in terms of math. If you are given some number, let's say some integer number, there are many ways to write this number in terms of a sum of other numbers, right? Arbitrarily many ways, right? And none of these ways to write that sum is wrong, right? It's just many ways, okay? So that's quite important, right? To keep in mind that these orbitals we obtain, and that also actually holds for Huckel and Hartree and Hartree-Fock, they are just auxiliary constructions for us to think about the true many-body wave function and the true nature of the molecules we are studying, and we have to be very careful when interpreting them. Okay, not all of them are directly linked to observables. We discussed this also in the context of the chemical bond, right? So I said before, there's no operator for the chemical bond. So this is a human projection, right? And we can describe and interpret that projection in terms of in ways that are consistent with quantum mechanics, but it's not necessarily the only way to do this. Okay. In fact, in my research group, we are currently developing alternative energy expressions for chemical bonds, which incorporate the quantum mechanics. It's also consistent with quantum mechanics, but they look very different. Okay, and yet they can be more accurate than let's say Hartree or even Hartree-Fock. And so, what is now the right interpretation of the chemical bond? Is it this method or that method? Right? It's all these methods attempt to describe a similar or the same concept, but it's not. There's no unique way of doing this. Okay, so you see here the outstanding role that the actual Hamiltonian and the postulates of quantum mechanics play in giving unique ways to quantify and define certain properties. Okay, other properties which humans have invented are not necessarily uniquely defined, and so you need to be able to distinguish this. Okay. Now, my rule of thumb is if you don't have an operator, then you either don't know this operator, right? There's no classical correspondence, which does not mean yet that there's no operator, or the observer you're trying to describe is actually doesn't have an operator, so it's not well defined. Okay, So that means there are multiple ways to describe it, which again does not imply that it is useless, nor does it imply that it is wrong to look at such concepts using the well-defined properties, right? So, for example, one interesting discussion is about the frontier orbitals and their role, and they form in some sense an exception, and there's some discussion, for instance, in the Journal of the American Chemical Society, and just, yeah. So to me, this is recently, but I just realized it's already 22 years ago. So Roald Hoffmann is the Nobel Prize winner from the Woodward-Hoffmann rules, right? He's still alive and kicking, and so they contributed a nice kind of paper, and in some so many theoretical chemists argue about the meaning of these eigenvalues and orbitals when there's not a unique solution but multiple solutions. So for the frontier orbitals, it looks as if they are much more unique than the other orbitals, and so you can argue about that. So the HOMO eigenvalue could be the ionization potential, and in Kohn-Sham DFT, strictly speaking, it's really a ground state theory, meaning that only occupied molecular orbitals are part of the procedure, and hence only they should be discussed. We should not be discussing unoccupied orbitals in a strict way, but in practice, we actually do. Now, how do they enter? They typically enter through the orthogonalization procedure. So you can have much more basis functions. You can construct these unoccupied orbitals. Your occupied orbitals change, and then the orthogonalization also affects your unoccupied orbitals. But they are not part of the Schrodinger equation, right? And so you can argue if they are actually meaningful. Now, as I mentioned before, in the beginning, people tried to get rid of orbitals altogether. So there is still something known as orbital-free DFT. This is a line of research where people try to really avoid orbitals and to develop improved approximations, in particular to the kinetic energy. So this would be still fantastic, because then you don't have to deal with orbitals, and so your computation costs would be much faster. Unfortunately, however, the predictive power is typically quite poor. Then there's something called density matrix theory. This is actually, it's quite interesting. If you recall, we defined our electron density by integrating out all electronic degrees of freedom except for one electron. Now you could do the same, integrating out all electronic degrees of freedom except for two electrons. And then you would basically have a bald R and a bald R prime, and that's a matrix, right? And so you can look at this electron density matrix. And this is, of course, a much more expensive, numerically expensive method, but it is very appealing in terms of its predictive power. And so if you wish, between orbital-free DFT and density matrix theory, you have Kohn-Sham DFT as a compromise in terms of accuracy and speed. So with this, I'd like to make a little break. We are at the end of this subsection of Kohn-Sham, of the subchapter, and I'd like to discuss for the remainder of this DFT lecture, I'd like to discuss density functionals, which means approximations to this exchange correlation potential.
I'm sorry, I have a question.
Questions?
Oh, yeah.
Seems to be the case, so let's resume.
Sorry, can't you hear me?
11:15.
Okay.
Anatole? Anatole? I don't.
Or Morris? I don't think you can change the slides, right? Okay.
No, after the break, I'll message Anatol. How about that?
Okay, perfect. Thank you.
Sure.
All right. So you need some parameterization of your exchange correlation of your Kohn-Sham potential, right? Which contains an exchange correlation potential. So here, this is this equation, right? So in the remainder of today's talk, we will talk about approximations to this, right? So you somehow assume some functional form. And this is what enters your Kohn-Sham equation. So this is the equivalent to the Hartree-Fock equation. And you have to do this for all your electrons, so that you can get your density, you can get your these two energies, and then you do this until you're converged. And once you're converged, you have orbitals, energies, the eigenvalue energies, and the electron density. And then in the last part, we discussed how you would use this to actually calculate your total energy then, as in this boxed frame.
Could you just go back to the last slide, I think, before that you showed?
This one?
No,
With this one?
no, it was the very last slide that you had before the break, I think. Here, yeah. So you would regain the NR, but in which formula would you regain that N?
In this top procedure here?
Yeah.
Oh, so you have this electron density, some initial guess.
Mm-hmm.
You solve for your eigenvalues and your orbitals, right?
Yeah.
Then you have new orbitals, and these new orbitals you plug in to calculate your electron density, as shown here.
I see. Okay.
Right?
Thank you.
Thank you for your question, right? So this was also in chapter 5 when we discussed the electron density. Whenever you have these single electron methods, such as Hartree-Fock or also Hartree, right? Your electron density is simply the sum. All right. We would like now to discuss functionals. Okay. Now, the most fundamental density functional, which does not have a lot of predictive power. It is similar to Hartree-Fock, but so it's not state of the art in accuracy, but historically, of course, this was a major step forward, and also conceptually, it's very appealing. This functional is called the local density approximation. Now, the LDA function. Okay. In the LDA functional, you presume that your exchange correlation energy can be approximated by this term, right? Which is defined as the integral of your electron density, and purely multiplicative. You multiply your electron density, you scale it, if you wish, at every point in space with another function, purely multiplicative. Okay. So that's, if that works, right, it's super elegant. This is something extremely appealing, right? And in this sense, it is local, meaning that whatever the value of this E xc is at R, it gets multiplied with the electron density at R, and it doesn't depend on other R primes, right? So it's just a product of these two terms. And this EXC, then if you take the functional derivative of this, then with respect to the functional derivative with respect to electron density, all you're left with is this EXC. So this is your exchange correlation potential also, right? For your Kohn-Sham potential, you need the, or for your final energy, right, you needed the exchange correlation potential and the exchange correlation energy. All right, so what is this E? Okay, now we want to, the LDA approximates E, it ignores all kinetic corrections, and it approximates E simply by the exchange and the correlation energy which you will get for an electron in a homogeneous electron gas. Now, what is a homogeneous electron gas? You can imagine a box, think of particle in the box, right? You imagine some box which has some background potential. Maybe you're applying an electric field. Forget about atoms. You just have a box with an electric field, and this field keeps your electrons in place. Okay, and now this background potential can be constant. Now, what are your electrons going to do? They're going to be constant too. And that's what we call the homogeneous electron gas. Okay, so the electron density in the homogeneous electron gas is just a constant. It does not depend on where you are, right? Now, in the LDA functional, we approximate this E to correspond to what you would get for the homogeneous electron gas. But this N here in your expression varies, of course, as you approach the atoms, right? If you have a molecule and not some box, right? And so at every point in space, we simply pretend that this would be the constant throughout your system, right? And this is the approximations that we presume that would be applicable, right? And of course, in reality, it's not. So we should expect some deviation, right? But let's see how well we do with this. So this is the idea, right? The values of this exchange correlation potential at every point in space of R, you evaluate this with the help of the local, so at the electron density at the same point, right? So we were pretending the electron density was homogeneous and independent of its local environment. And one can also show that you can actually write our E in terms of two contributions. So it's just a sum. One is the exchange and one is the correlation potential of the homogeneous electron gas. Now, the exchange part is actually well known. Okay, this, as the name would suggest, this is what comes out of Pauli's exchange rules, and Slater and Dirac, long time ago, have shown this already. That in fact, for the homogeneous electron gas, the exchange potential is simply proportional to the electron density to the power of 1/3, okay? And there's a proportionality constant. So this is easy, right? We can use this. What is a bit more tricky is the electron correlation of the homogeneous electron gas. And it turns out that the best thing to do is to run a quantum Monte Carlo simulation. And this was done by Seppali and Alder in the 70s or 80s, I think. And they also exploited for very large and very small electron density. They exploited known analytical limits. And with this, you can fit this electron correlation function to different values of the electron density in the homogeneous gas, right? So your constant value, as your constant value of the electron density increases, your electron correlation potential changes. And they obtained this, and there are multiple fits to those numbers. There's a fit by Vosko, Wilke, and Nusser, a fit by Perdue and Zunger, and a fit by Perdue and Wang. Right? In principle, if you use quantum chemistry software and you want to do an LDA calculation, then your results will depend on which fit you're using, and often you can select the fit, or by default there's some fit. For instance, in the CPMD code, which is one of many quantum chemistry codes, there's a default LDA option in terms of the Perdue 1 fit. Okay. Now, how does this electron correlation look like? For large, let's look at this function. It's this epsilon c, right? And it is plotted here as a function of a variable, which is actually inversely proportional to the number of electrons, right? So it's the inverse electron density here to the power of 1/3. This is what's known as the Wigner-Seitz radius. So this is some averaged spherical radius of each atom. There's a way how you could measure an atomic radius. And you can plot this as a function of the electron density, right? This Rs. So Rs is a function of the electron density. The larger the electron density, the smaller Rs. So down here you have the large values of the electron density, right? So you get a lot of electron correlation. And then as the electron density becomes smaller, you get you go outward, you reduce the electron density. And you see this, if you imagine this radius to be meaningful, then you can roughly expect this to happen as a function of the distance from the nucleus, right? So your electron correlation energy of your electrons roughly decays with the distance from your atom, as shown as in this function. Now you can fit this again. So these numbers come from the quantum simulation, the quantum Monte Carlo simulation. And now you can fit this, for instance, with such a function or such a function for large and small values. And like this, you can then get a numerical prediction. Okay. Now, so in other words, what you see here is, right, that this thing is known, you just plug it in here. And this thing is known, you also plug it in here in terms of this fit, and they both depend on the electron density, and with some 1/3 exponent being 1/3. So there's a nonlinear change of your electron density, and you integrate over this product, and then you have this expression. Okay. So then all terms are known in your formula. Right, there's our formula here. Right, we know this guy. Right, we've parameterized it. We also know this one, right? And then we know we know these guys with the electron density, and we get it. All right. So what about the predictive power now? If you use this parameterization and you make some predictions, often you are as good as Hartree-Fock, right? But it's also cheaper than Hartree-Fock because you don't have to evaluate all these exchange terms. And so this is an advantage. And then it's also easier to interpret in terms of your electron density, just like we discussed this here, right? So this is very appealing. There is one point, right, which was made, is that the exact potential is supposed to decay inversely with distance outside the electron density. But with LDA, actually, this is not possible. And so it decays faster than it should be. It decays exponentially. And this is a problem then for large distances, meaning for regions where you have very little electrons, you should not trust the LDA so much. Now, intuitively, that makes sense because you're approximating things as if things were homogeneous, right? And so as if you had a lot of electrons, then when you have a lot of electrons, that's a good approximation. When there are very little and your molecules, let's say intermolecular forces intervene, then these electron densities are very small, and then subtle changes can result in qualitatively different results. And this is where LDA will have problems. So this tail of the electron density is crucial also for the ionization potential. This is where the valence electrons sit, right, in the large distances. And so when you ionize your molecule, this is where the electrons will change. And so it's the first property where you would see such errors. So the ionization potential, surface interactions with surfaces, or stability of negative atoms, this is difficult for LDA. They also overestimate intramolecular forces. So if you have two benzene molecules doing pi-pi stacking, or DNA fragments, right? The stacking of the DNA bases, there are strong intramolecular forces which are typically overestimated by LDA. Vibrational frequencies, phonons and solids and molecular geometries are typically okay with LDA, but you will find that the geometries and the lattice constants, everything is a little bit shrink too much together. So LDA likes to pull the atoms together. In other words, it slightly overestimates the electronic contribution to your total energy. Typically also energy differences between s and d orbitals are bad. And so this results when you have high spin, low spin complexes where these electronic states would be competing, like the 4s and 3d orbitals, then you would have a bad prediction of these trends. And so you could be missing on important magnetic properties. So you might be really qualitatively wrong in predicting magnetic effects. Typically also reaction barriers are very poorly described. So you should really stick to the geometry minimum. So for instance, the H2 plus H reaction, so just a change of one hydrogen to another one, has a negative reaction barrier. So this means that where there should be a barrier, you have a minimum, okay? And so that is, of course, highly problematic then. So here you see some numerical results for various solids, the deviation from experiment with LDA, shown here in green, and then there's some correction you can do, and you see that overall this is a small percentage, less than 1%, right? This LDA with this nonlinear core correction, and you see that overall this does pretty well. If you ignore all electron correlation effects and you basically just go with Slater's and Dirac's exchange, then you would get this red curve, right? And that's much worse. So electron correlation matters, okay? You would have much more difficulty describing trends in lattices. Here's another example of the bulk modulus of materials. Now you see the bulk modulus and you see the experimental number in black. And then again, LDA is closer to the experimental numbers than this pure exchange part. You also see here formation energies in various solids, and LDA is shown as a triangle, and it's giving pretty good estimates. Now, why does it work so well? Well, these are is a selection of properties where LDA works well, right? We discussed properties where it doesn't work so well here. Now, why does it work so well for these cases? First of all, this exchange correlation contribution is the smallest. Right? So our original idea to put the dirt under the rug, right, was also meant to say, look, this is the smallest part. Let's we would expect this to contribute the least. So trends might be right. Now, LDA is simple, but it still fulfills many important requirements. Okay, so it's not a bad thing, and it's actually, if you look at it from the chronological thing point of view, right, it's much more sophisticated than Huckel theory, and so and also Hartree theory. So there's a lot of good physics in there, and this is this can be seen as one of the reasons why it would work reasonably well for these simple properties. Now, there's some major error cancellation between exchange and correlation. So this can also help to basically keep the exchange correlation contribution small. And so this can be sort of beneficial, right? So here's an example of the energy components in the manganese atom. So this is the kinetic energy here, Kohn-Sham kinetic energy. This is the electronic Hartree contribution from core and valence electrons and from valence and valence electrons. And this would be the exchange energy, and it's of similar size as the electron correlation. So this would even, roughly speaking, this cancels, right? And so this is really something we are exploiting here, right? And you see that the kinetic energy is very large, and this is the Kohn-Sham kinetic energy, which we didn't know, right? And for the full electron density, right? This is why we introduced these orbitals again. You see a single percentage error you make on this would be huge in energy. A single percentage error you make on the exchange or correlation is much smaller. So that's why you really wanted to have orbitals again. All right. Now, there are many shortcomings of the LDA functionals, and they have been discussed quite a lot in the literature. Here's still some sort of overview. One of the problems is something known as the exchange correlation hole. And this is something, this is a projection, and this is an average over the entire atom here. And you see it should look like, so it's a property of this exchange correlation potential. And it should look like this full black line. That's the exact solution for toy system. And LDA would or also local spin density. So this is the dashed line, right? And it's quite wrong. However, if you average it over all angles around your atom, then it still looks reasonable. So this is why LDA is not catastrophic, but you see there's quite some important physics missing. I will not go more into the details here. This is just to illustrate a little bit that if you dig deeper, you can readily identify strong deviations from truth. So there are some problems with the change of with the number of electrons, with the change and the energy and the potentials. There's some self-interaction, right? The double counting, which we haven't corrected for. One of the, as we mentioned before, is that D and F functions are problematic. The tail is difficult to describe with LDA. And this is this exchange correlation hole you see on the right. So one suggestion then, which really gained some momentum in the 80s, but the suggestion actually is quite old already, made by Hohenberg and Kohn themselves, was to include also gradients in the exchange correlation potential, right? So we could try to do this, but it turns out that if you just do a simple Taylor expansion, things get actually worse than LDA. And what people then did was to include gradients fitted to other things, right, or obtained from other systems than the homogeneous electron gas. And these so-called generalized gradient approximations, also known as GGAs, they carry acronyms such as this: the BLYP, the P86, the PW91, PBE. Typically, these letters stand for the first letters and the last names of the authors that developed this. So BLYP is the Becky, Lee, Yang, Pa functional. So these are four famous theoretical chemists. P is Perdue, Perdue Wang. This is Perdue, Berg, and Ernsterhof. And if there's a number attached to it, typically it's the year in which this functional was published. Okay. Now, one of the most famous functions is this PBE, the Perdue, Berg, Ernsterhofer functional. It is a functional which was not fitted, but rather obtained by obeying theoretical constraints, such as the LDA functional. So what this consists of is you now write you approximate the exact unknown exchange correlation energy by this PBE term, which is defined again as a sum of exchange and correlation. And the exchange part contains again the LDA function. And then you see now there's this scaling function on top of that that's multiplied in. Okay. So this here we know electron density times electron density from LDA, that was 1/3, right? Raised to the power of 1/3. So in total we have raised to the power of 4/3. And this is the LDA exchange correlation coefficient. And then there's this F function. And this is the contribution of the authors that they describe F as such here. And what you see is that there's a bunch of terms. And these terms contain, for instance, this mu, which is just a factor. But in here you have this S, which depends on the electron density gradient now. Okay, so this is where the gradient enters your exchange correlation potential. And similarly for the electron correlation, you multiply in an additional term here. In this time it's an additive correction to the LDA factor, to the LDA correlation function, and it looks as here, and the derivation of this is very complicated, but the important part is that these terms were not found by fitting or trial and error, but rather obtained by obeying exact constraints. And this functional is actually improves the predictive power tremendously. So the vibrational frequencies are as good as those from LDA, but now you actually have reaction barriers. Okay, they are typically still underestimated, right? They're still not perfect, but at least you have qualitatively, you can describe chemical reactions. Unfortunately, the intramolecular interactions are weaker. So this is basically as much as LDA overestimates, GGA now underestimates the intramolecular properties. Now, John Perdue, who's one of the fathers of these functionals, is a professor in New Orleans at Tulane University. He proposed a hierarchy for these functionals, and they are shown here. There's a heaven of chemical accuracy, right? So this would mean your prediction errors on the order of the experimental uncertainties. So that is really the dream of a theoretician. If you're as good as the experiment, you're then, for all intents and purposes, in terms of that particular experimental setup, it doesn't matter if you do the experiment or if you do the calculation. Right? So then you could supplant the experiment by the calculation. And that in itself has its merits. It also has some disadvantages, but that is then more of a philosophical question. Now, he proposed this hierarchy, so that the most accurate method here, so akin to solving Schrödinger's equation for full configuration interaction, right? So for the full many-body wave function problem, we should be able to do this within the density functional framework if we follow this hierarchy. And the worst we can do is this Hartree ansatz, right? This is the SCF idea, and we can work our way upward here, right? By including more physics. So this would be then the first rung is the LDA function. What have we done here? We have the Slater determinant, and we have that exchange correlation potential, which we just discussed. Then you add gradients on top of that, and then, for instance, this PBE function, which we just discussed. This should improve your accuracy, and this is what we call rung 2. Now we can also introduce second-order derivatives, okay? And that is then something like the kinetic energy, right? Remember, that's the second-order derivative, and one of the most well-known so-called meta GGAs is the TPSS functional. If you go beyond that, you can include the explicit other orbitals, right, in your Kohn-Sham potential. Now, this is then the same as what you do when you do a Hartree-Fock. You're including, through the exchange operator, you're including another orbital in your potential. And so this is why these functionals are called hybrid functions. So hybrid meaning they hybridize the Kohn-Sham idea with putting the dirt under the rug with the Hartree-Fock exchange operator. And then finally, rung 5 should be something where you also include unoccupied orbitals explicitly, and that connects us to some of the most advanced quantum chemistry methods that go beyond Hartree-Fock. Okay, so this is then also fully non-local, because your occupied orbitals might be somewhere completely else, and so this should be the kind of physics you want to get the highest predictive power. Here is an overview in terms of predictive power for various solids. In particular, 20 solids were studied in this paper. This is the Journal of Chemical Physics in 2008. What you see here are now the functionals. Some of those acronyms, hopefully you remember now. This is the LDA function, the PBE function, right? So this is the first rung, second rung. The BLYP is also a second rung, a GGA, but it performs even worse than LDA for these solids, right? Now, BLYP is a little bit more empirical, and it was fitted on individual free atoms, and it works better for molecules than for solids. And so this is reflected in this figure. So what you also see is that if you go from this PBE to PBE0, which is a hybrid functional, so you're going from this PBE here to this PB0, then you see a clear improvement in the lattice constant of these solids. Now, these authors actually showed that AMO5, which is also a functional which contains, actually it's in between LDA and GGA, is also capable of getting similar accuracy. Right? Now, AMO5 doesn't work so well for molecules, but for solids, you see it's on par with the performance of such hybrid functionals. And that is quite interesting, right? Because it would suggest that this hierarchy, as you see it here, is not rigorously true. Right? So it's an approximate hierarchy, if you wish, right? It's still very helpful. In many cases it holds, but not always, right? And it also tells you that the ways how we approximate the Kohn-Sham potential in DFT, these ways have not been fully maxed out in terms of what could be done. Right? Maybe there is still a way to really come up with the exact expression or something very close to that, which gives you highly accurate predictions while being very computationally efficient. Now, here on the right, you see similar trends for the bulk modulus, which is sort of the vibrational capability of the solid. So generally saying, in terms of properties and first, second, and third or fourth rung of Purdue's ladder, you can think of structures, energies, barriers, band gaps, intermolecular interactions, and electron transfer. And here you have a little overview what you would typically expect for these functions. Outstanding challenges of DFT represent weak interactions and spin ordering and excited states and charge transfer. So if you apply electric fields, this is difficult. Of course, also combinations thereof, as well as chemical reactions. Here you see an extreme case of a failure of DFT. These are many different density functional approximations. They are predicting the elastic modulus of elemental niobium in the crystal. And you see here the C44 component in this elastic modulus. The experiment predicts 310 kilobar. And your best functional is here at 214. Okay? So you're missing 1/3 of the property. So that's quite catastrophic. Now here's another example, more from the organic chemistry. This appeared a couple of years ago in Chemical Engineering News, and it was based on a JAX paper, which you see here, 2015, where the authors had studied in great detail a multi-step reaction, this condensation of this carboxy group with the double bond here. And so they studied this with spectroscopical methods. They mapped out the entire reaction surface. You see this here in black. And then they did, with using various density functionals, each one represented by a color, they calculated the energies along this path. And you see that depending on the functional, you can get whatever you wish. Okay, and so this is was very frustrating that these calculations are not so meaningful. It turned out later on, one of our collaborators showed that actually most of this deviation does not come from the functionals, but rather from the solvation models these authors use for their calculations. But that's a separate issue, right? So you can think generally that the predictive power of atomistic simulations was shown in this work to be quite questionable. And so in general, we should all try to do better than that. With this, I'm at the end of my slides. I see that we reached noon. I still had some papers from the literature which were recently published by my lab, where we also studied, looked at different density functionals. I will show you those tomorrow. And then I can also still give a little overview once more on the entire course. And you will have also the opportunity tomorrow to ask some more general questions regarding the exam or what is needed or other chapters in the course. With this, I'd like to thank for your attention, and I still wish you a good afternoon.
Anatole, Julian asked a question about topics for tomorrow, if that's okay.
Come again, did you say something?
Yeah, there's a question in the chat from Julian.
Oh, thank you. All right. Okay, let me read that question. What always makes it difficult for me to follow physical chemistry is to connect it to practice, the part that stings and bangs. If we have time tomorrow, could you tell us a bit more about the importance of the calculations for the practical applications? And for example, how they are important for new synthesis. Okay, I'd love to tell you about that tomorrow. I hope we can create some connections then. Yeah? All right.
There's just one thing, sorry.
Yeah.
Are you going to upload the slides for Hartree-Fock and DFT on Adam?
Yes, I will.
Because I would also like to discuss tomorrow a couple of things on Hartree-Fock, which I thought were very complicated.
All right, I'll upload it today and then you'll have it.
Perfect, thank you.
Thank you. Bye-bye.